Okay, so in yesterday's class, you were looking at replica-based okay, replica-biased LDO. Okay, and in this particular LDO, we have uh, like a loop which is not directly regulating the supply of the oscillator, but is regulating a replica of the oscillator. So right now, I just use our R replica, and this is your V reference supply VDD. Okay, and the same thing was transferred to the same VDD supply is there, and this is your actual VCO. Okay, so now this is MR, MM is the main one. Let me just call this as V out 1 and this is V out 2. Okay, this we had. And what we looked before was V out 1 means by VDD of S, this was SVDD by 1 plus S by omega out. I will write it again. So 1 plus loop gain of regulator. Okay, where now your SVDD will correspond to your replica device. So RDS, sorry, R replica by R replica plus RDSP of, sorry, RDS of regulator replica, and your omega O and omega out were before, which was CC times, sorry, let's put it as RA times CC omega A, and omega out was RDS R in parallel with R replica with C of out. So let me make the small signal diagram for this block. This was GMA. This goes to okay. So R replica. This is VDD. CC RDSR. This one will be GMR. So let me mark this as plus minus Vx. So this is GMR times Vx. This is R of the amplifier. Okay, and this one is your V ref minus plus. What else is needed here? This is C out, and this is connected here. This node is V out 1. Okay, and on the other side you have so RDSM. This is our VCO, and GM main times you can say, okay, this is V out. So GM times V out minus VDD, right? V out 1 minus VDD, and this is CD right now. Okay, I just wrote it again so we do not miss anything here. Okay. And loop gain of regulator is A times A naught by 1 plus S by omega A into 1 plus S by omega O. Okay. So I am going through it again because there are a few things which are still to be discussed. So we looked at that V out 1 by VDD is something like this, where your omega A used to happen here and somewhere you had omega O with respect to omega. So this is mod of V out 1 by VDD, and regulator bandwidth is somewhere in between. Okay, so this is for the PSRR, which we see with the only the replica part right now. Now the thing is that if we want to improve PSRR, we can make omega O dominant, but making omega O dominant actually comes with a larger capacitor which you need to use for the means having a stable loop. Okay, so the other way, so what in replica what we are doing is, so we still maintain V out 1 by VDD. Okay, another thing which comes, so if you look at two things, what is the translation from V out? So if we have this kind of transfer function from VD to V out, if we have some other transfer function, maybe a low pass filter, right, which can be V out. So this is, let's say, if this is, I am just putting a if there, if V out 1 by V out 2 is something kind of this, you do not need to compromise on the larger capacitor, on the size of the capacitor in the replica, in an actual regulator. Okay, and this is actually what is happening when you use a replica based regulator. So look the transfer function, which is V out 2 by V out 1. Okay. So V out 2 by V out 1 is, that is simple, right? GM times, this is just V out 2 by V out 1 is GM times your RDSP in parallel sorry, I write RDSM or what? Yeah, I use RDSM in parallel with RVCO into 1 plus S by omega D, where your omega D is equals to 1 over RDSM parallel RVCO times CD. Okay, please, you have to find it actual. I just wrote it. There are some terms which I have not used. Okay, so the actual will be what, if I just write the equation here, that your minus GM times V out minus VDD minus, sorry, plus V, this is V out 2, so VDD minus V out 2 by RDSM is equals to V out 2 by, so you have actually the other part also, that's why it will be there, V out 2, so this is 1 by RVCO plus SCD. Okay. So the easier way to do is that, so this is GM, so this is V out 1. The one equation which I wrote here is only tentative. I'm not written the exact. Sorry, this is only through Vout2 by Vout1. The actual thing what you want is Vout2 by VDD. And Vout2 by VDD will have two terms. One term is coming because of the Vout1 and another term is coming directly through VDD. So you can see that part. You got that, right? So one is coming through the GM, other is coming directly to the VDD part. Okay. And this can be simplified. This is what we need. So what you can do is Vout1 minus VDD, this part. So you can have minus GM by Vout1. Okay. Is something wrong here? But then, yes, yeah, this is right, no? So you can have this VDD minus 1 plus 1 by RDSM 1 minus Vout2 by VDD is equals to Vout2 by. I do not want you to get scared from just the equation, so you can just substitute here Vout1 by VDD from the previous part. Okay. So what happens is that the final transfer function, which turns out will be something depending on gains and all, you will have like this, where if I make my omega d as a dominant pole, omega d actually lesser than my omega a, then all my peaking is gone. Okay. And if omega d becomes the dominant pole, then the regulator bandwidth will also become omega d itself. Okay, so let me draw it as a VDD over so this one is omega d and you will have somewhere omega a. Okay, and the regulator bandwidth will also be omega d if it becomes a dominant pole in the system. Okay, now if this is the case for V out, so in the above transfer function I use V out 2 by VDD, and we know that the phi out by so let me just say omega PLL, right? This is phi out by V out 2. V out 2 is nothing but the control voltage of the VCO here. Okay. So now if I ask, this is omega D, right? Which is regulator bandwidth coming as such. So where should I place omega PLL with respect to omega D to have a better PSRR? Forget what is actually there, but for better PSRR, what shall I do? For better PSRR, this should exist here. Okay, can you do it? Stability will be a problem. So the thing is, for better PSRR, you need to have omega PLL greater than your omega D. For stability, you have omega PLL lesser than omega D, where omega D is right now on the regulator panel. Okay, so this is the trade-off which you will face. So there is a way which comes with the. So the question is, can we decouple regulator bandwidth with the PLL bandwidth. Pardon? Hmm. If we have a separate regulator, no, but all the control, it should be controlled through the regulator itself. So, okay, let me, if let me say, see what you're saying. So I have a VCO, right? And this is the supply to the VCO, VDD. And this is the V control of the VCO and whatever phi out or V out, whatever you want. Let me write it as phi out. That's a better part. Okay. What you are saying is that if I can control regulator for this and I have this V control, this is what you try to say, right? What, when can you do it and what's the problem? What's the benefit of this? Huh? If you are not using ring, we can do, but we are using ring. So this is what you're saying is right. If you're not using, if the control voltage means if the control for the oscillator is not coupled to the supply, then you can do it. But if the control to the oscillator is coupled to the supply, which will be the case in conventional ring oscillator control, then it's difficult here. Okay, and this actually gives rise to this gives to the way for a split tuned like regulation in split tune PLLs. So I will go into split tune later, but right now I leave this open because going for the split tune will require to understand more of the loop filter parameters. Okay, we will come back to this thing, but right now this is the problem. No, so whichever current, so see, you have an inverter. If you are using a current disturbed inverter, you are using this, right? And what it means is look at the whole control, then you will. So, okay. So let me. This is complete control of a current disturbed inverter, right? Now you get is if you are using a current disturbed converter, you look on the supply noise here, 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 all supply noise. So you are not avoiding any means. The one which he was saying that you have a regulator separate where it doesn't interfere with the control at all. That is not the case with the current disturbed inverter. You need to convert V to I. Whichever control voltage is coming from the loop filter, you need to convert that V to I. How will you convert the V to I? You need one conversion there. Okay, let's say I put a regulator on this current disturbed cell. Who is varying this part? Sorry. How will I vary this part for the control? Okay, so this is what I am saying is the current. So from the loop filter, what I get is only the voltage. This is V loop filter. Let's call that. Okay. Huh? Okay. So let's see that too. That means all these things are. So let's say, are you going to do this as a current? So this is VDD. Okay. Let's say it is a regulated VDD, and I push into this. right? And so now what I can do is I can have this. You want to do this? So what will be the hmm? Why? I can put a cap. Means okay, putting a cap there. So, okay, let's say I put the loop filter to VDD. That also I did it. Let's say this is VDD. So what will happen in this case? Now, okay, you regulated VDD, right? If you regulated VDD, what will you use? Means what is the output? Means there is some current which is coming to VDD, right? So if this is, so let me just say, if the input which you are giving, this is VDD regulated, there is some VDD which is coming into your chip which is not regulated. What will you have in between? A pass transistor logic, the same thing which we have uh, used. Okay, this. Now this is an extra control, means this is regulation reference, right? This is what you can do effectively. Now, any trade-off in this, any, means there's nothing comes for free as such, we all know. Pardon? Why more power? Oh, let's say these, the current in these, the current in this branch is, I am saying is negligible. I am using a large ratio. Pardon? Swing at loop filter output? No, let's say that is, so the thing is in a locked steady state, right? Only small ripples will be there. Let's not bring those ripples right now. So steady state, the voltage is constant. It only changes when you change the frequency. Any trade-off. So what decides the frequency of the oscillator? Huh? So okay, let me just ask you this. So this is VH and this is V low. So what decides the, given you size the inverter once, what decides the frequency of oscillator? VH minus VM. Now, if you are using these MOSFETs as current sources, M0 and M1, what did you do? With respect, so initial input supply was this, right? So how did you change the VH? Uh, no, I do not. Means inverter not equidistant is not a problem. Inverter is means effectively here inverter is equidistant from VDD regulator with respect to ground, right? So that's not the problem. See, you are now earlier you were having only one current source with respect to the given VDD supply and the ground and the inverter high voltage. Means whether you are regulating current or you are regulating voltage, in the end, effectively it is doing the same thing. So now you need to have overdrive for this and overdrive for this with respect to actual input VDD. Right now I am even neglecting the bottom one. Okay, let's say I only control the top current source. So this is a kind of a cascaded regulator. I have one regulator which gives me a good PSRR, and the second one is also a kind of a regulator. It's like, right? So effectively, I lose on the headroom, and as soon as I lose on the headroom, I lose on the frequency, higher frequency. Pardon? For very low frequency of operation. Yeah, then I will come with an argument. Then why you are investing more power? See, if you increase your VDD for the same amount of oscillation amplitude, then you are losing on power. Okay. I mean, there might be places where you do this, but it depends what is the final goal. Okay, we will come to the split tuned of the PSRR with the split tune regulator when we are going with the loop filter in more detail. There's a lot in the loop filter which I haven't covered. It's like active loop filter and the split tune loop filter. We will go now after this. Okay. So, any questions so far? Okay. So, the other part which we were discussing yesterday was your designing our replica with respect to the VCO. That was where we left. So, sorry. So, we have an actual VCO. So look at this. We had an actual VCO and we modeled this VCO. So let me VH. We model, so let me call this as V control itself. We model this VCO effectively with a resistance in all our analysis, right? V control, which actually consumes the same average DC current as the VCO consumes. Okay. Now we know that VCO there will be swing at the V control if it is just a current voltage source. There will be current swing. So if I give a normal volt, let me just see this. If I give a DC voltage source to V control, some DC voltage source to V control, what you will see are current ripples. IVCO will have the ripples in the system. Okay. Now, when we model in our all the loop analysis, we said, okay, this is only a DC resistance. There's nothing else there. Okay. Now we want to replicate the same thing in the regulator here. So using the same VCO would be too bad because you will be consuming a lot of power as per the VCO. So what we can do is, the one option is, so if this is W by L size of, let's say, each inverter, what we can do is we can just scale it down. We make it, let's say, by M. And this will become, in our modeling, R VCO times M. Right? So you can do this. There is no problem doing this. But the actual problem is that you will still be having the you will still be having the ripples on the supply, on the control voltage itself. Okay. Which is now the question is whether it is good or bad, that you can check it. Surely, if you are having a ripple in the system, your loop is always working. It's not, means you will see some more glitches, not that it's stable. It's stable in the sense, okay, the loop is stable. For incremental changes, you will see ripples at the control voltage so see this also, that if you are having any ripples here, if you use a VCO, the same ripple will get translated, and depending on the multiplication factor, it is again getting multiplied. It's not that flat DC voltage if your frequency is not changing. Okay. So the other, or the one of the better ways of doing this is use a diode connect model of the VCO. Means scaled and diode connect model of the VCO. scaled diode connected model of VCO, which actually consumes the same current. Means if I have a scaling factor of M, I have the same resistance M times R VCO. The only thing right now is that you will not have any kind of ripples in the regulator path if your reference for the regulator is not changing. And this actually gives a better PSRR. You can like that. Means better ripples if you're looking for any translation from this to the jitter. Fine. Okay. You can look at the whole reference paper. This is paper somewhere in 2004 or 6. Okay. 2004, I think, by Ilad Ali. That's the paper. Where they first introduced at that time. Okay. So, any questions so far? Pardon? Why not spend the same power in the... No, your replica is scaled. How much? So the thing is, yeah, so you always make a comparison. So if you find that spending a 20% more in an actual regulator gives you a better PSRR, you would go and do that. But normally it turns out that is not the case. No, one other thing, right? If you are spending more power, let's say if you are spending more power in case of the actual regulator, the only thing you can do is you may move this, right? Having a larger bandwidth, whereas your PLL bandwidth is still the down. Means PLL bandwidth is still sitting somewhere here, and you move the frequency by spending more power in the regulator to the right hand side, right? But means it depends how much do you move, so you may still have the peaking. You are not, so the thing is you're not getting the benefit which you get by having an extra pole where you suppress the ripple a lot. Okay, means you can surely make that do that analysis that whether investing more power is more beneficial or splitting as a replica and the other one gives you more benefits. And in the replica bias one, you will surely have the matching issues. This is as good as the replica matching is there. So you cannot also always make a 1:1000 ratio if you want to reduce power. That will not be good. Okay. So this actually we will return back to this topic after we are done with the loop filters and others. So next we'll move on the loop filter. And so let's look at one assignment. We can do the other one tomorrow or sometime. Okay. So okay. So the first question was that in this, just bring it here. In this loop we have PD. So the actual question is, you have PD, loop filter, and a VCO. Okay. So this was the actual loop, and I asked to draw the any steady state estimate block diagram. Any problem with that estimate block diagram? Right? There is nothing. Okay, since I wanted to derive the frequency transfer function about omega out by omega in, I put 1 by s in the feedback. Okay, so this is with respect to omega in and omega out. Had it be phi in by phi out, I will just put it as kvc over s. Okay, and from h omega s to h phi of s, did you directly write it as, did you find the transfer function or you directly wrote it? Huh? I didn't get it. You find the transfer function, right? Means could you not always make I want phi out by phi in? Yeah, loop itself is clear, but the other thing is phi out. You can always do that. This, right? Phi out is s times omega. Sorry, phi out is integral. So omega out by s and omega in by s. So you do not even need to write the loop transfer function. It's direct from there. Okay. Sorry. So the next one is derive the steady state frequency error for an input delta omega. So this is the transfer function for omega out by omega in. You need to find a steady state error. Either you can find omega out minus omega in transfer function and find that, or you can find the final settling of omega out and then look at the error. Okay, so I just found the final delta omega. If I give delta omega in, what is my final output frequency? And this is using the final value theorem, right? We know this part. Final value theorem. So it turns out to be omega out is equals to delta omega in. So your steady state error is 0. Okay. The next one is what is the steady state control voltage in the loop. So you have the transfer function for the control voltage. It's the same thing you can do here. Any problem in doing this part, right? No. So you have means partial fractions for the S domain, and finally you find this. And the plot is, I think, one exponential itself. There is no problem. Okay. And the E part is the steady state control voltage. So if it settles to the same omega n, then you know what the control voltage should be. It should be just like the final delta omega by KVCO. Okay. The other thing is what is the settling time for 0.1% frequency error in response to step. So this also comes to the exponential settling, right? Everyone got this thing, right? I do not see any issue, no, right? Okay. The next one is okay. So the next, let me just make the block diagram here. You have phase detector, charge pump. Okay. So this is reference voltage and this is the input and output. So I think the only problem might be to define the control from. So if T delay is 1 nanosecond per volt, 1 nanoseconds for one delay cell. So for 3 delay cells, it should be 3 nanoseconds, right? If you change the control voltage. So how did you change this delta T to output? Did you get confused with any time here with the KVCO thing or something? No, right? It's directly it's delay thing. So you have 3 nanoseconds delay, and delay you can convert the gain by in the phase factor, right? So this one is converting the voltage to the phase using how much delay you have. Okay, phi out by phi in again is the same simple transfer function. Determine the value of the capacitor to achieve the jitter transfer function bandwidth of 1 megahertz. This is also, it's a first single pole transfer function. Okay, and in case when everything is connected, reference and input are shorted. Okay, so you have the same frequency, your transfer function is 1. So the question would be, what's the benefit of doing that? You can get a multiple phases for the delay cell, whatever you are having. Okay. So the next one is problem 3. Okay. This one, okay, for this, you have phase detector, loop filter, and VCO. So this is the block, sorry, there is a divider, divide by N, and phi in to phi out. And I asked to derive the phase transfer function phi out by phi in. Okay, and here the thing was loop filter is Sorry, that is simple RC filter. Determine the loop filter pole achieved to have a loop phase margin of 90 degree. This is again writing the transfer function and getting phase margin and the bandwidth. Okay. Any problem in this assignment? I do not know. Nothing there, right? Okay. Then you have a type 2 PLL design, which is, okay, here the loop filter changed to, I'm just writing in case you do not remember, R2CR1. Okay, input and output. This is the loop filter, the same thing as before. Okay, so how did you do it? I think somewhere, did you get it right or solve it completely, or there was any problem? This is just a solution, right? You know the phase margin is this, and they say phase margin is 65 degree, loop gain equals to 1. That you can work it out. Okay, you find omega u by omega z, unity gain bandwidth, find omega u by omega p also, and then you have, the only thing is, in order to find R2 and R1, you need to make some assumption what the capture value you want to use here. Okay, so here I took it as 1 nanofarad, you can use any. So which one? It's a passive loop filter itself. So you are using only, so the DC gain is, so you have a 0 here. There is 0, right? So initially you had only one single RC filter, right? This one actually increases the, no, if you have only simple RC filter, then you have, then there is like a 90 degree phase margin which you approach. Okay, not 90 degree. So if you have only this simple RC filter, you have one integrator, and this simple RC filter, phase margin depends how your RC filter is there, right? The other one is you introduce another 0 in the system, so you are more relaxed on the bandwidth and the phase margin part. You can have only R2 and C. Yeah, you can do that part. It's okay. So all these things, if you go back to the, go back to this hold-in range, acquisition range, and all those things, there you will find this what these loop filter values are at infinity. And so, okay, let's see the, I will show that thing. So consider this loop filter. What is the value of this one? This is R2 plus 1 by SC by R1 plus R2 plus 1 by SC, right? So I have 1 plus SC R2 and 1 plus SC R1 plus R2, right? These are transfer function. And surely your pole is coming first, right? So the transfer function for this is this. This is the loop filter transfer function. Okay, now consider only the one which you had before. Which one did we use? Okay, we have in the first filter which we had was this, right? Which is 1 by 1 plus SRC. So the transfer function for this is depending on where the R is. Let's say even if it is at the same location, something, it will be like this. So the difference between these two actually will tell you that where how much this thing pull-in range and your the one was, what was the, no, hold-in range and tracking range are the same, huh? Locking range. So this loop filter value at infinity will actually define what these values are. I think we check, we can find with that, right? Yeah, that's the difference which you will see. Okay, Means other than the phase mark, and the other one which you are considering is which is 1 plus SRC by FC, right? So this loop filter will have actually 0 comes, okay. So it again depends. The pole comes first and then you have a 0. So this is something you can say like this, right? So these two, we started with this, then we wanted a 0 to have something at a higher frequency. We went up to this. Then we say, okay, we do not have an infinite DC gain. Let's go to this. Okay. Which one? Okay. First order RC loop filter infinity is 0. No, you need to see the whole means just putting the final value without looking at the whole thing, I think may not work out. So what you are saying is if the loop filter value is becomes uh, 0, SC. No, but this is at the, yeah, means if the loop filter infinity value becomes equals to 0, I think just check that out exactly when you, no, expression is exist, I am pretty sure about it. So what is the tracking range? Is right. That is the pull-in range, locking range itself. So okay. Uh, so what's the means? It's like it turns out to be the locking range is going to be 0 if the loop filter infinity means as per this. Okay, I need to check that with the means when I am trying to means 0 is like it will tend to 0 if it is coming that way as such. Only if it is an exact, then only it can work. And it depends on the phase detector, where phase detector gains another part also. Okay. Yeah, you can have that. Is there any advantage for no? So okay, let's see. Uh, for the loop gain transfer function, consider the two cases. No, so in one case, what we are, if we are only using an RC filter, we have something like this, right? And 1 by S is coming from the KVCO over S. So if this one is coming much like if my KVCO over, where should I plot it? Okay, so if this is KVCO over S, so the total which you may see is the combined form of this will be minus 40 dB per decade, right after the loop, after the pole. Okay, so the thing is the unity gain, if you are, wait a minute. So, okay, let me just write it to see. It's not going here. Okay. So, your loop gain is 1 over 2 pi ICP 1 by, so this is 1 by 1 plus SRC into KVC over S. This is the loop gain, right? So in this particular case, yeah, means unless your this pole has to be basically beyond the unity gain frequency which you are considering. Whereas, so let's do that part. So if this is my 0 dB line, my pole, okay, should be like this. That is where the pole should come. Whereas in the other case, what you have is ICP, you get another 1 plus SRC2 by 1 plus SR1 plus R2 times C KVC over S, right? So here you have your pole comes first, right? So you will have the same, then you have a pole, and if you have a 0, then you can have this thing, right? R1 plus R2. So you can have bend means the, so whether this is of any use, is that a question? Means you are getting, this will help you in changing the noise transfer function. Okay, means how useful is, you need to see which noise becomes dominant. Okay. Anything else? So the other one is basically on this tracking range. You want to discuss tomorrow, or okay, it's already time is close. Huh? Yes or no? Okay, let's discuss that part tomorrow. I think that's the part which was quite confusing.